Hey, it's Mathman Dan. I am at the Encina Wastewater Authority. I am meeting here with Bruce, who knows all the ins and outs of how this works, and they are taking all the wastewater and sewage from a lot of North County here in San Diego, and they're making it clean enough to send back to the ocean. And you were telling me a little bit about this process. We're actually standing at kind of the final stage here.
Correct.
So what happens when the water, first arrives right out of the sewer pipes to you guys?
Well, Dan, as we saw, or we will see later on, we have samples being taken 24, so all day long, and they're analyzed in the lab for total suspended solids and other analyses.
I know one of your chemist, Joel, was going to help us out with that. He's going to actually take a sample and measure how much waste is in there, how much solid waste compared to liquid, basically, right?
Right, exactly. And so what happens there is we're measuring the treatment throughout the plant by doing these samples, and here we are at the very end of the treatment process called secondary treatment, where we're producing the water that will finally go out to the ocean.
So you told me that at first you just remove a lot of the solid stuff that's easily removed, and then after that you actually have biology at work.
Correct. Out here in the secondaries, it's kind of a two-stage process. So we send microorganisms that we settle out in this particular tank back to an aeration basin, and the aeration basin is fed the primary effluent, which is what we call the food. So we have a F to M, food to microorganism. It's sewage coming in.
Yeah.
And that's actually food for these microorganisms that are settling out in this final secondary process. And we try to get those at a 2-to-1 ratio, or a 0.5 ratio, which is basically 2 pounds of microorganisms to each pound of food.
And that's the right ratio to make the natural processes happen the way you want them to?
Correct, and that's what we kind of shoot for. There's other things we shoot for depending on time of the year and that, but that's generally what we're looking for.
So I know that's some of the math that was involved, because we're talking about how your chemistry guys would take samples and determine what the ratio was, and that would in turn determine how much of the microorganisms you guys need to add or maintain anyway.
Correct. In the aeration basins, we're actually giving the microorganisms all the oxygen that they would want to reproduce. It's basically the best environment they could have. They have all the oxygen and all the food, and obviously they're going to reproduce. So every day they're producing more and more. And we measure that concentration, and at the end of the day, through the lab, we get the concentration of the food. Through us in the field, we get the concentration of the microorganisms, and we can determine how much we need to waste. And so we will set a wasting rate based on trying to meet that 0.5 F to M, or food to microorganism ratio.
So you're constantly measuring and then sort of recalibrating and making sure it stays kind of at a steady balance. Is that fair to say?
That's very fair to say. Yeah, exactly. Typically we are at a very steady state, and so we may make an adjustment of 50 gallons a minute on the wasting rate.
Oh, really?
Or something. Sometimes we don't even make an adjustment, but we're constantly looking at that, and as long as we stay stable, we're good to go.
I know it looks like the control room, I saw some graphs on the screen. Is that kind of some of the stuff that they're measuring? I saw some graphs moving along the wall.
Exactly. We're trying to our return activated sludge, which are the microorganisms going back to the aeration basin to meet the food coming in. We're trying to pace that with the flow of the wastewater coming through the plant. So we typically have a 25 to 30% return of activated sludge rate. And we will adjust that. And that just basically says at any point in time, we're going to return 25% of the flow, which is concentrated microorganisms, back to the food that's coming in.
Oh, okay.
So we get that ratio and we keep it nice and steady.
I found it very fascinating that most of the work done here is by microorganisms, not by mechanical filtering. I mean, mechanical filtering seems to just take care of a little bit of it. Most of it is by you guys maintaining this biological balance, constantly measuring the ratios and making sure that biology does its work.
Well, you're exactly right, and this is the really most important part of the treatment process is monitoring and farming the microorganisms and keeping them in the right condition, the right concentration, and the right population of microorganisms to help us meet the treatment that we're trying to get.
And we're standing over a tank at the last stage, and on the edges of the tank where the water is actually getting ready to go to the ocean, it looks crystal clear. And your chemist guy measured it for us, and it was, I don't know, 90-something% improvement, more than that actually. I'm going to figure it out back in the studio for real, but
Okay.
it was an incredible improvement. I was impressed.
Yeah, I think he measured us 6 milligrams per liter when it was coming in at something over 300. So if you do the math, it's going to be close to 98%.
And we will do the math.
Okay.
Bruce, thank you very much for being with us today.
Okay, Dan,
I learned a lot, and I hope everyone else does too. We'll talk a little more about this back in the studio. You know, when we were over there talking to Bruce, one of the things I found most amusing was that everyone working there referred to, you know, all the stuff you flush down the drains and comes out of our houses, they all referred to it as food because it is for their microorganisms. Anyway, I actually was really impressed with the operation they've got going on there. They serve 300,000 people, and I looked this up. They treat 36 million gallons of water every day. That is amazing. But one of the things he was talking about mathematically, he was talking about this ratio, and where this occurs, basically the stuff comes in from the sewer pipes right into their facility, and he said that, you know, they easily take out the big stuff, but then there's lots of particles of solid matter still in the water, and that we mentioned is it first goes into this aeration tank, and the aeration tank is where all these microorganisms are. They have to have, you know, lots of oxygen for them to live happily, and lots of food, as they mentioned, coming in. Well, they don't have a shortage of that. And then the microorganisms in there take care of everything as long as they keep this ratio in about the right place. So I'll show you that in a second. What happens after that is they go to this secondary tank he mentioned, and then the microorganisms and some of the matter basically clump and sort of sink to the bottom, and they call that sludge. So there's still microorganisms in there, the sludge, and what they do is they then can send some of that sludge back into the aeration tank if they need to get more microorganisms in there. So that's how they're doing it. They're constantly evaluating the ratios, and if they need more of the little critters, they take them from that second tank and push them back in the first tank. And he said sometimes they don't have to do this, and sometimes they do 25 or 30%. So anyway, I brought in some pictures of what these little guys look like, these microorganisms, and they really are tiny. You cannot see them with the naked eye. You have to have a microscope. But he mentioned several different kinds to me. These are called rotifers, so that's one example of the guys down there eating the food. This is an amoeba. They really have those. These are called ciliates. They have little tiny hairs around them, so they have things like that. And this is a filamentous bacteria, as is this one. And this is some other, this is another rotifer, I could say some other critter. So they have all these little guys down there eating all this stuff, and it's actually taking care of the sewage in a completely natural way, so they don't have to do any mechanical stuff to it or chemical stuff treatment. It's actually taking care of it, just how nature intended, I suppose. And he mentioned this ratio, so I was going to show you a little bit of math involved there. So we're going to go, and he talked about an F to M ratio. And he said it was 0.5. So F is food, M is microorganisms. And so I wrote it as sometimes you see ratios written. If you were in a math class, you would see probably the ratio written as a fraction. So very similarly, what we want to see is a fraction like F over M equaling 1/2. So let's say, we'll make up a sort of hypothetical situation here, just to see the kinds of things they have to think about. Let's say they went and measured the water, and you know, this is what they do this several times throughout the day, he said, actually. I kept referring him to as the chemist guy. He has to go, his name is Joel, actually. He goes and tests the water to see what all the levels are. So let's say they go in, and just a hypothetical situation, let's say that the food, which are these suspended solids, let's say that came out to be 320. And I don't know if you heard him say the units they were using were milligrams per liter. So like if you took a liter of water, that would be 320 milligrams of the food. And let's say that they did the same thing and tried to find out how many microorganisms are in there. They do this by weight also. Let's say that came out to be, let's say 585. Again, I don't know if these are not actual numbers. We're just doing a hypothetical situation here. But if you did this and you went on a calculator, actually divided this out, this comes out to be about 0.547. It's a little on the high side. So that would mean that they have a little too much food. They need some more microorganisms. So this is where they would take some from the second tank and sort of ship them back in to make the balance, you know, back where it's supposed to be. So how do they know how much to put in? And this is where a simple little math problem comes in. And you know, they have computers to help them, but this is the math going on behind the scenes here. So what we really want is a ratio to be exactly 0.5, or we could say 1/2. So I'm going to use, just like you would in an algebra class, I'm going to use x for the amount of microorganisms we actually want. So instead of writing 585, I'm going to put X, since we have 320 of the food, and I want that to be exactly 0.5, or I could say a half. And if you do a simple cross multiplication, have you guys played with that? I'm guessing you have if you do an algebra class. If you multiply these diagonal guys, 320 times 2, and these two diagonal guys, x times 1, they have to be equal. So that tells us that x would have to be 640 to make this happen. So all you would have to see is, how far are we off? We would need, well, we're at 585. We actually want 640 milligrams. So we would need an extra, let's see, so that 55 milligrams of food for, or not food, rather, microorganisms to eat the food and keep the balance in check. So if you convert this, I actually did this ahead of time just to see, and there's more math involved here in converting, right? But what I did was I converted milligrams to pounds, and I converted liters to gallons. This comes out to be about 0.0017 pounds of additional microorganisms in every gallon. You might think, like, well, that's not very much. 0.0017 pounds, that's hardly anything, right? Well, these tanks were huge. I remember they're processing 36 million gallons of water a day. So I don't know the size of their tanks, but I just took a guess. What if it was like 8 million gallons? I mean, these tanks were very, very large. If you multiply that out, that means you'd have to stick in about 14,000 pounds of microorganisms to keep the balance in check. So they're doing this all day long, continually recalibrating and adjusting these ratios. And it really is, this is a proportion we've set up basically, two ratios that are equal to each other, just like you might do in an algebra class. Another thing he mentioned at the very end of my interview with him there was about the percentages. So this is not particular to the little feeding frenzy they have going on. It's just percentages. But I did say I would do the math back in the studio, so we better do it, right? So a little percentage, he said that he thought, if you remembered right, that they measured the contaminants coming in at 300 milligrams per liter, and when they left, they were 6. So let's see what kind of improvement that actually is. So what we're going to do is we're going to take the ending amount, which was 6. That's very, very little. 6 milligrams per liter of food, as they called it. And then at the start, he said they had over 300. So let's just go on the conservative side. Let's say we had 300. What kind of improvement is that? And you don't even need a calculator. You can actually do this by hand. If you do the division, this comes out to be 0.02. And if you remember anything about percentages, if you take a decimal like 0.02 and you want to express it as a percentage, that is 2%. So of all the original waste that was mixed in that water, only 2% is left, which means you actually got rid of 98% of it. And I believe that's actually the exact number he said that they go over. And I think they actually do even better than this. They get beyond 98, 99%. It really was amazing how clear that water was coming out after they let those little critters do their work. So one other interesting fact about this place is the sludge I mentioned, the solid stuff. I mentioned some of it gets used, pushed back into the aeration tank to help out with the feeding. But the rest of it, they actually recycle and use for fertilizer. In fact, they recycle 100% of it. So nothing of the waste coming in, I was going to say nothing goes to waste. That sounds funny, but it all gets used, which is very impressive. They won a bunch of awards. And anyway, if you want to check the place out for yourself, if you live in San Diego County, you might have seen it. It's in Carlsbad, right off the 5 freeway, right off the coast. So, Mathman Dan here. I am at the Encina Wastewater Authority, and this is where much of North San Diego County's wastewater and sewage flows. And here, they attempt to clean up. Well, not attempt, they do. They clean it up well enough to send back to the ocean, which is amazing, and I've seen a little bit of the process myself. But we're here with Joel, one of their chemists, and well, there's lots of chemistry, right? But there's also a little bit of math in there too.
This one's the math.
That's what we want to look at. We're going to show you a little bit of the math that goes in. This is something very important that he has to do every day. We're going to try and figure out, well, a special number. This is a sample of the sewage that was coming right in here, right?
Right. This is the influent reaching the plant, and basically we're analyzing this to test the total suspended solids. It's the organic material in the water stream.
Okay.
And then test basically what we're doing through the process and how we're treating that and cleaning it up.
So you're looking for just one number that's a ratio of the solid here, and then
exactly.
Depending on what that is, that might affect things that get changed in the process of when it gets cleaned.
Exactly.
Okay, so this is something you guys do every day?
Yeah, every day. We'll test a composite sample at each of the levels of treatment and basically see if the numbers are within our permitting ranges and what we're putting
Hopefully
out.
They are.
Yeah, definitely do a good job here. And
so one number we're after is a ratio of the weight of the solid compared to how much liquid it's in, and Joel's going to show us how they do it. So what's the process here? We have a solid sample.
You have a sample and a pre-weighed filter paper.
Okay.
And we'll basically take this on an analytical balance, get weight to 4 decimal places.
That's pretty accurate.
It's a very accurate scale. Yeah, we'll take a certain aliquot, which in this case we're going to use 100 milliliters of the influent.
Okay, so
and filter it through.
Doesn't look too clear.
It's not very clear. It's a little murky. Basically, just turn this vacuum pump on and use some pre-filtered deionized water to rinse it through.
Nice and clean.
Nice and clean. Make sure nothing's on there and pour this one through.
This is going to catch any solid stuff.
Right. You can see it accumulating on the filter paper.
Oh, yeah.
Everything else will pass on through. We'll make sure this is rinsed nice and well.
Get everything out of it.
Exactly.
Okay.
And when this comes out, we'll put it in 105 degree Celsius oven for an hour.
Try it out.
Put it in, take out the pre-dried sample and reweigh.
Yes, you have a little worksheet of numbers here.
Right. We have the tare weight of the paper and the dry weight of the paper and the solids.
And then we can figure out how much the solid weighed.
Exactly. Using that, we'll subtract the tare weight of the paper, find out the weight of the solids that accumulated on there, and then multiply it using the aliquot of 100 mils to figure out how much per liter. Basically, it's milligrams per liter suspended solids.
And then if that's a good sample, that should be the ratio for the whole batch coming in.
Right. Yeah, it's a composite sample, so it's pretty representative of an entire day, and we can have a good idea of what's coming into the plant, and then we'll do this at the various steps to make sure we're removing the appropriate proportions, and
that would be good.
What's going out is up to par. And
what kind of numbers would you typically see?
Anywhere from 200 to 400 for influent, and at the primary level, I mean, it's the first stage of treatment, it already drops down to around 50.
And what about when you guys are all done with it, you ship it back to the ocean, what kind of numbers would you see?
Typically less than 5 milligrams per liter.
So from 2 to 400 to 5.
Exactly.
That's pretty impressive.
We do quite a bit of treatment here, and the water that comes out is definitely a lot less, lower numbers.
No, I saw a little bit of the process. I am very impressed. But so this is one of the many measurements you guys have to take monitoring through the process to make sure it works nice and smooth.
This one's done daily, and it keeps our operators on the toes and make sure that everything's running smoothly. Yeah, exactly.
Joel, thank you very much for showing us a little bit of the math involved here. I had no idea how impressive this facility actually was, but I am impressed now. So
thank you very much.
Back in the studio, we are going to actually check his math, and I'll show you exactly what kind of calculations he was doing to come up with his numbers. We don't have to check his math for his sake. He was doing very well. No, we're going to show you a little bit what he was doing. It really was fascinating there, and I think you can actually, I think they give tours actually. You can go check it out if you want to. And like I said, you might think like, I don't want to go to a sewage treatment plant, but it was actually quite fascinating. So anyway, so he's an official chemist there, and he was responsible for the testing. So what I've done is I stole some numbers from his worksheet he was actually doing, and so we're going to figure out how he came up with the numbers he did. So the first thing is a 100 milliliter sample. He was using some official language there, so I wrote solids on the filter here. He called them suspended solids. He filtered the original liquid through, and it trapped all the solid stuff floating in there, and so there's the weight, and he has a very accurate scale. This is 4 decimal places of accuracy for grams. It's a very, very precise measurement. And then he talked about the tare weight. So a tare weight, T-A-R-E, means weighing the filter without anything on it. So they did that beforehand, and he had to dry it all in an oven to make sure there's no moisture that was going to add to the weight. I mean, very, very precise. Once he did that, we just simply subtract these, and we get the weight of the solids that are sitting on the filter paper. So that was 0.0353 grams. Pretty small amount. But what we really want was this final number he was after, and the units he said were milligrams per liter. So I'll show you what we have right now if we just do a simple ratio, which is the first thing he would have to do. So we'll take our net weight here, it's 0.0353 grams, and we'll just make a ratio out of it. We'll just divide it by the sample, which was 100 milliliters. And if you do this out, you get 0.000353 grams per milliliter. Well, that's a valid measurement, if you will. I mean, it's a correct ratio, but it's not the right units that he wanted. So we need to convert the units. And this is something that's come up on our program before. This is a really useful skill you can use to convert anything. I mean, metric to normal things, or, you know, weights and liquids and anything. This can convert things as long as you know the conversion factors. So that's what we're going to do. So keep this in mind. This really is helpful for other things too. So what we're going to do is we're going to start with the number we have there. This is the grams per milliliter. And remember what our goal was. We want milligrams per liter. So we're going to do some math here. And we want to end up on the far right here. We're going to end up with milligrams per liter. So I'm leaving some space. And all we have to do is multiply by some conversion factors. And the whole idea of this is multiply by something that's really equal to 1. So you don't actually change the value, but use the measurements that will cancel the ones you don't want and keep the ones you do want. So for example, I don't want grams sitting there on top of that fraction, so I want to multiply by a fraction that has grams on the bottom to get rid of it. And what I really would like is milligrams on top. Well, all you got to think of now is, do you know anything that's equivalent between grams and milligrams? And yeah, you got to know a little bit about the metric system, but 1 gram is 1,000 milligrams. So that fraction is equal to 1, basically. It's measuring the same thing on the top and bottom, and the grams cancel. And we are left with milligrams on top, just like we want. All right, one more. I got milliliters on the bottom there. I don't want it. I want to get rid of it. So I'm going to put milliliters on top of the fraction. What we do want is liters on the bottom, so I'll put that there. And all you got to think is something that's equivalent. Well, same old metric system here. I know 1 liter has 1,000 milliliters in it. So watch the units again. Milliliters cancel, and you're left with liters on the bottom, just like you want. Now you got to do is do the math. And apparently all we have to do is multiply by 1,000 twice. Well, that's not too hard. What you end up with is exactly 353. So this is the number he actually reported on his worksheet. It was 353 milligrams per liter. And he mentioned, you know, how, on average, what kind of numbers do you see when this stuff's coming into their plant? And he said from 200 to 400. So this is, you know, 3,500. That's right in the ball range of what he was talking about. So how well do they do after they work on it? So another thing we can do is look at the percentage improvements they make at this plant. And they have several stages, and he tests at different stages. But on his notebook, one of the stages was after what they call primary. That's like the first stage of cleaning that they do. So after the first stage, I checked his notebook. So this is called primary. The number they ended up with was 46.8. So they got quite a big reduction, actually, but we can figure out percentage-wise exactly how much that is. Here's a little practice with percentages. All you have to do is divide the smaller number by the larger, and we'll find out what percentage that was. So 46.8, divide it by 353. That comes out to be about, I did it ahead of time, it's about 0.133. So if you learn about percentages at all, you have to remember that that's a decimal number. That's not the percentage itself. You move the decimal 2 spots to make a percentage, or you can think about multiplying by 100%. So that's really equivalent to 13.3% approximately. So what that means is after the first stage, only 13.3% of the solids are still there. So if you take out off of 100, that means this is actually an 86.7% reduction just after the first stage. And as I mentioned, they have biology working on this. So there's several stages it goes through. They have, I can't remember all the different creatures they have, bacteria and such, munching on all this stuff. And by the time they are done and ready to send water back to the ocean, it really is clean enough to do that, by the way. I saw it with my own eyes. They get it down to, he said, less than 5 milligrams per liter. So less than 5. I assume the worst case 5, if that's their limit of what they can send back to the ocean. And in that case, I did a percentage again, 98.9% reduction. So they virtually get 99% of all that stuff cleaned up before they send it back to the ocean. And when I was there looking at my own eyes, it looked crystal clear, which was amazing.